Hello everyone. Welcome to another talk in our webinar series. I'd like to remember that this webinar is also being streamed live on YouTube, so you can find the link on our website or access it on our YouTube channel /LIneA MCTI. Today we have Vivian Miranda from the University of Arizona presenting the talk entitled The Connected Universe, Relating Early, Intermediate, and Late Universe with Cosmological Data. So Vivian, thank you very much for accepting our invitation and being with us. The floor is yours.
It's a pleasure to be here. I always told friends that I think this LIneA Webinars is one of the best ideas I've seen in Brazil in the last few years in science. Much before, much than the pandemic. This idea that we can, exchange knowledge using, virtual seminars. I think that's great, and especially in this new carbon footprint era. So it's a pleasure to be here. I have lots of collaborations with the DS Brazil that I'm trying to increase over time. Right now, I work with 4 students from São Paulo, students of Marcos Lima, Rogério Rosenfeld, but I'm always open to work with students from other members of the DES Brazil. We have lots of ideas. We're doing lots of developments for DES Y3 here in Arizona, and that is a great opportunity, to share code, share knowledge, and share, leadership. So, the opportunity to bring leadership to DES Y3, more opportunities to bring leadership to DES Y3. Uh, so today I'm going to talk about a couple of ideas that summarize my research in the last few years, and I hope that by the end of this talk I can come across three main like topics or three main sentences to your mind. So the first one is that the universe is, broadly speaking, divided into three eras that I'm calling early, intermediate, and late. I will define what these eras are and like what are the boundaries, what are the main properties of this era. And the second is that there are still physical uncertainties in the dynamics of all these three epochs. And third, and more important, that these uncertainties can all propagate and affect the current expansion and the current structural formation of the universe today. And why this is important? It's important because Brazil is participating in a lot of optical surveys, DES, LSST, and DESI. And these optical surveys are trying to use the current expansion, the current structural formation to understand the microphysics of dark energy. So, let's start defining what I mean by the first phase, the early phase, which broadly speaking, it goes from the inflationary era, which is the first phase of accelerated expansion. This first accelerated expansion, we know that was not caused by cosmological constants because inflation ended, and then and that is sufficient an argument to know that it's not a cosmological constant. And it goes up to the recombination era around 300,000 years after the Big Bang. The main dynamics of this era is caused by an expansion that is dominated by radiation and has radiation as a very important component, and therefore expansion was too fast to allow structure formation to grow. The universe were ionized during this epoch. It's the first phase of ionization in the universe, and ended when the universe becomes recombined for the first time in its life, the recombination era. And that is like a golden era to be probed and constrained by the cosmic microwave background. So the second one, which is the intermediate one, goes from the recombination around 300,000 years to reionization around 1 billion years. This is in a phase where cold dark matter dominates, and therefore expansion is gentle enough to allow structure formation to grow. This is an era where massive neutrinos become non-relativistic, and that has big impacts on the current expansion and structure formation. And it ended in the called reionization, where the universe became ionized for the second time in the history. And in this epoch, the ionization was caused by gigantic POP3 and POP2 stars. If you know astronomy, we know that most of the elements heavier than hydrogen and helium are used in the interstellar gas to cool the gas, and there were not so many of these elements in the past. Therefore, the gas could not cool down. Stars were very massive and emitted a lot of ionized radiation, and that radiation was enough to ionize the entire universe. And that's kind of the golden era to be probed by 21 centimeter experiments. And finally, the late universe that goes from 1 billion years up to today is a universe that during the first half, it's still dominated by cold dark matter, but then it makes the transition to a second phase of accelerated expansion. And now this phase might be explained by cosmological constant. It's also a phase where we have a lot of nonlinear evolution of a structure formation. Gravitational collapse becomes highly nonlinear. There's also a lot of baryonic effect that makes it harder to extract cosmological information. But on the plus side, we have lots of probes, optical probes to measure to constrain this epoch. And that's the golden era of optical astronomy. So, we have all these epochs with widely different dynamics. So how can we use data, and how can we create a coherent story that explains all these epochs, all these different dynamics, all these different scales? And one way to do that is by considering different types of observations. So here I'm summarizing 4 main observational schools that we use in current cosmology. In the future, in very near future, we are going to introduce 21 centimeters, but I'm excluding for now. And the first one is the observations of type 1a supernova and local measurements of the Hubble constant. The second school is observations of the cosmic microwave background. The third one is gravitational lensing of optical galaxies and counting of nonlinear clusters. And the fourth school is the so-called baryonic acoustic oscillations. And the exercise I'm going to do now is the following. I'm going to take a subset of these schools, for example, CMB and BAO. I'm going to see what kind of universe these subset of schools prefer, and I'm going to see if these are compatible with the universe that is preferred by the remaining set of observations. For example, using local measurements of Hubble constant and gravitational lensing of optical galaxies. So when you do this type of comparison, you start to see very interesting problems or features of the standard model. So in this picture, I'm showing you on red, and if you're colorblind, that is the circles, the dots that are circles, how the predictions of the Hubble constant from cosmic microwave background and BAO varies over time since the last 15 years. And you can see that it's going towards like 67 kilometers per second per megaparsec. And I'm comparing this against the blue or star dots, if you're colorblind, of the local measurements of the Hubble constant. And you can see that they are disagreeing, and disagreement is increasing with time. So therefore, if you believe that the standard model of cosmology is given by the cosmic microwave background, then we have a universe that locally expands way too fast in comparison to prediction. As you can see here that I also put in blue measurements of gravitational waves that is still have very large error bars, but it's very promising in the future, just to exemplify that we will have in the near future other ways to check and to probe this disagreement. So a second disagreement comes from this strange parameter that's called S8, and that is a parameter that mixes expansion rate and structure formation. So just to give an intuition, what S8 means, suppose you have 2 universes, A and B, and they have the same amount of cold dark matter in it, then a universe that has higher S8 is a universe that is more inhomogeneous, at least in the scales of 8 megaparsec. But there's another, you can also interpret S8 as the follows. Suppose you have 2 universes, A and B, where you fix the amount of inhomogeneity in this universe. Then a universe with higher S8 is a universe that has more cold dark matter in it. And here I'm comparing the predictions of S8 from cosmic microwave background against many optical surveys, DS being one of them. And you can see that the surveys all measure an S8 that is lower than predictions. The error bars are still large, but at some point in the future, we'll be able to combine those probes, and it looks like that this can be a very interesting type of disagreement between these different schools of observers. So by doing this exercise, we can conclude that if we truly believe that the universe, the standard model of cosmology, is the universe that is preferred by cosmic microwave background and BAO, then the universe that we actually see is a universe that expands too fast, and it's either too homogeneous or has too little dark matter. And you might think that such results implies that dark energy, which drives the current epoch for cosmic acceleration, is not given by the cosmological constant. But this talk, it's a cautionary tale against this conclusion, because there is still a lot of uncertainties in other epochs of the universe that we need to make sure we understand before we can state that the dark energy is not a cosmological constant. So I will just give a brief introduction of correlation functions, which is a technicality that I will need throughout this talk. So you can ask how to extract information from the cosmic microwave background, which is this nearly isotropic radiation in the sky. So we do this through the two-point correlation function. So this is a map of the temperature and isotropies of the CMB. So we are taking the monopole out. And the way we extract information is by taking a radio telescope or a satellite and measure in a certain position the intensity or the polarization of the light. Here I'm just assuming one polarization state for the didactics. And we're comparing this to the intensity and the polarization state in a different area, different location in the sky, and I'm fixing this angle between them and make averages all over the sky. So when you do this, you get the so-called correlation functions, and you can have autocorrelation functions of intensity of light, autocorrelation functions of the polarization of light, or cross-correlation between temperature and polarization. So that's how we extract information. But we are physicists, and we like to work on Fourier space. So here I'm showing the Fourier transform of the intensity autocorrelation function. And I want you to understand two aspects of this Fourier transform. First, that on small L's or large scales, we have some kind of a plateau which can have different amplitudes, and then we have this series of oscillations that have well-defined positions and well-defined relative amplitudes between the different harmonics, and we can use these amplitudes and these positions to extract information about how your universe works. In terms of correlation function, we can do a very similar exercise with structure formation. So just to simplify and the didactics, so let's assume we have a fictitious dark matter telescope bought by Apple, and that we can point this dark matter telescope, at one position in the sky and measure, for example, an overdensity, a halo, or a void, or an underdensity in the sky. So we can make the correlations between the overdensity and underdensities in certain positions with overdensities and underdensities in other positions, and we can make averages over the skies at fixed angle, and then and by doing that, we get the autocorrelation functions of the cold dark matter. And here I'm showing a very famous animation from Max Tegmark in the 90s, and I want to emphasize the following. So in the bottom, we have the Fourier transform of this dark matter autocorrelation function. On the top, we get the Fourier transform of the autocorrelation of the CMB. And the parameter that I'm varying here is a parameter from inflation, this accelerated expansion within that happens within the first second of the universe. So there's a lot of interesting conclusions from this plot. So first, physics from very early universe can affect structure formation today. That's an obvious conclusion. But the second one is that whatever changes the universe they have to change the CMB and the matter power spectrum in a consistent way. And that is the harder exercise in current cosmology. I understand that there is consistency across scales in a single redshift. Small and large scales come from the same perturbation theory, and consistency across time that the CMB and the local universe have to be consistent with each other. So with that, I finished my introduction, and I'm now going to talk about research that I have been doing in each of these epochs. It's a good stop for questions. Okay. So in this early part, I'm going to talk about inflation, and I'm just going to, which is this phase of accelerated expansion in the universe. And I want to ask the question, like, why do we need inflation? Why inflation? Why do we need to, include those this epoch of accelerated expansion of the universe in our standard model? And I'm just giving you two explanations why. There are more, and the first one is the horizon problem. That this problem is the following: if there is no inflation, and then the area in the sky that has physical contact is points that are separated by a maximum of 2 degrees. And that's a problem, because you can ask why points in the sky that are separated by 20, 30, like 90 degrees look the same. Why the universe looks isotropic if only 2 degrees patches can be in causal contact? Why the universe is isotropic? So that's one problem that inflation solves. And the second problem that I particularly like a lot is that inflation produces the correct seeds for a gravitational collapse. The seeds that has the correct statistics and coherence in them. So here I'm showing two possibilities that were very popular in the 90s of physics that can create those types of seeds that later on will collapse into galaxy, planets, and us. So one is inflation, and the other one is cosmic strings. And you can see some interesting differences between them. The first one is that they have a first peak that has a difference in phase of pi over 2. The minimum of one is the maximum of the other one. And second, cosmic strings, for example, only produce one oscillation in the cosmic microwave background, and why inflation produces a lot of oscillations. And the fact that we do observe these a lot of oscillations with WMAP, Planck, and South Pole Telescope and ACT is an indication that we need a type of seeds that has an statistics that's called a diabatic perturbation, and they're coherent in the sky, and inflation can produce this while many other explanations can't. So I particularly like this problem that inflation solves. And in the standard model of inflation, we have a primordial pulse spectrum, a Fourier transform of this primordial seeds of over densities and under densities that it's close to a power law. And so here I'm just showing what a power law is. And it has two free parameters, an amplitude and a tilt. And these are two of the 6 free parameters inflation of the standard model of cosmology. And physics after inflation that will transform this power law in these oscillations that we see in the cosmic microwave background. So this is the standard model, and it works great. But I want to show you that this is not the only possibility from inflation. Inflation can be more complicated. So here is one example of models that have been working in the past where inflation produced not only two types of power law. It has a difference in amplitude between large and small scales, but it also produces oscillations, damped oscillations. So it has a phenomenology that is way richer than the basic picture of the power law. And I can give a whole talk about this, but I won't. I want to ask different questions. I want to ask you two questions. The first one is the following. So what do we understand better? Do we understand better inflation, or do we understand better the physics of it after inflation? So let's assume that we understand better the physics after inflation. Can we use the data itself to reconstruct what the inflation primordial power spectrum should look like? And the answer is yes, and we have done this. And then we will try to reconstruct the power spectrum from inflation. It's interesting to know that the CMB data from the Planck satellite actually prefers a broken paraloid, prefers a primordial spectrum that has difference in amplitude between large and small scales. So inflation can be more complicated than the basic picture. And so knowing that there is uncertainties in the predictions of inflation, that inflation can be more complicated, I want to ask the following question: how these uncertainties propagate to our understanding of the late universe? So how early and late universe can be connected to each other? And they can be connected via the predictions of the Hubble constant. So as I told you, the CMB has this Fourier transform of the autocorrelation function of intensity of CMB lights. And this autocorrelation function has these oscillations that have well-defined positions and well-defined relative amplitude with respect to this plateau at large scales. And inflation can change this, can create a difference in power between the plateau and these oscillations, and therefore it can change the prediction of the Hubble constant. So we have checked the impact on these features. It's a small impact, but it does shift the Hubble constant towards even lower values than the standard model of cosmology. So that's an example of how inflation and the late universe can be connected to each other. So there are more ways that the early and late universe can be connected. One way is through the calibration of the sound horizon. So we know that the sound horizon of the CMB, the angular sound horizon of the CMB, it's around 2 degrees. But in order to convert this to predictions of the Hubble constant, we need to calibrate the physical scales of the sound horizon. And that requires an understanding on the physics of the universe and how the universe expanded before recombination. So what if the universe, our understanding is wrong, and the universe is more complicated before recombination? Can that affect the prediction of the Hubble constant? And if it's so, how can we falsify models or falsify universes with complicated physics before recombination? Well, the answer for the first question is yes, that can change, that can be more complicated. And the answer to the second question is that the CMB has two important scales. It has the sound horizon scales, which tell the position of the peaks, but it also has a different scale, which is the damping horizon, which tells how these oscillations decays in L. And we can use the measurement of these two scales that comes from wildly different physics to probe different models of universe with complicated early universe dynamics. So I'm giving two examples of such models. One is, what if the universe has more radiation than predicted? For example, come from more types of neutrinos. If you put extra species of neutrinos that are completely thermalized, you change the expansion rate, you change the calibration of the sound horizon, and therefore you change the predictions of the Hubble constant, and they have a perfectly degenerate linear degeneracy with each other. We know, and if that's the case, how can we falsify these models? Well, we know that neutrinos, they're decoupled from everything, and therefore when they propagate in the acoustic oscillations that generate the CMB, they propagate with the speed of the light, with the light speed. While we know that photons in that era, they have an effective mass because they are coupled with baryons, and therefore photons have an effective sound speed that is lower than the speed of light. And therefore, if you start with some inhomogeneity and propagate this inhomogeneity, you get neutrinos going further than photons, and that will feed back into the gravitational potentials, because remember, this is in a phase where radiation source gravity that will generate phase shifts and amplitude shifts in the CMB that we can falsify, we can observe. There are interest, and in fact, the CMB doesn't like this explanation a lot. There are other ways that we can go around this. You can make neutrinos with self-interaction that lowers their sound speed. This is an active line of research. And with that, another explanations, for example, early dark energy, and that's also an interesting line of research that we are going to explore in the DESI tree. But with that, I finished my part of the presentation that I'm going to talk about the early universe, and I'm going to the intermediate universe, and that's a good time for a question. Questions? Okay. So in the intermediate universe section of this talk, I would like to talk about reionization, which is the second phase of ionization in the universe, when the universe became ionized for the second time. And that was caused by these stars that introduce a lot of ionized radiation. But from the ELM point of view, the problem is the following. Suppose again that we have the cosmic microwave background photons and we have the radio telescopes, but between them we put a sheet of free electrons, and we want to understand what this sheet of free electrons will do to the autocorrelations of temperature and the autocorrelations of polarization. And just to summarize it changes in a way that allows us to reconstruct the optical depth that this sheet of free electrons will introduce at each redshift slices. And doing that, we can try to use the data to reconstruct this evolution of optical depth, this evolution of opaqueness. And at least in the Planck 2015 data, when we tried to do that, we discovered that the data would actually prefer extra sources of ionizing radiation that were not taken into account in the standard model of reionization, that assume that only POP2 stars are relevant. And there are updates in Planck 2018 that I can give a whole talk about this, but I would like to answer the following question. So given that reionization can be more complicated than usual, how uncertainties in reionization can be connected to uncertainties in the inferences about the early universe? So we investigated that, and we realized that the magnitude of the step in the inflationary pulse spectrum that we observe and explain the last section actually depends on the physics of reionization. So if you change the physics of reionization, you're going to change the amplitude that we infer from the data. So that's one way where inferences in the intermediate and early universe can be connected to each other. So what are the ways that intermediate and late universe inferences can be connected? So there are very interesting models in the literature that assume that dark matter, for example, decays into radiation, a small portion of it, from like 5 to 10%. And at least from the CMB side, if you decay dark matter into radiation, that's basically the opposite of what neutrino does, because neutrino, they are radiation and then they become non-relativistic, become like cold dark matter, kind of cold dark matter. So this is basically the opposite. And we know that by doing that, you can change the prediction of the Hubble constant and the prediction of S8 from the CMB towards more acceptable values. So that's just an example on how intermediate and late inferences can be connected. There are other ways that I explore is that, as I told you, neutrinos do the opposite of decaying dark matter does, and therefore neutrinos tend to lower the values of the Hubble constant that towards like from 67 to 64, and that's something that it's not allowed by BAO and the local measurements of the Hubble constant. But if you recreate dark energy that is kind of relevant between redshifts 1 and 2, where there are not a lot of supernovas to probe its equation of state, then these models of dark energies can undo the changes of neutrinos. And if that happens, then neutrinos become favored by the standard model because neutrinos can damp the structure formation, can lower S8 predictions from the CMB, and it's exactly what we need. So it's another way how the intermediate and late universe can be connected. Inferences can be connected to each other, not the physics. Inferences about the physics can be connected. And with that, I go to the last section of the talk. It's about the late universe, where I have more results, and that's also a good time for questions. Come on, ask some questions. Okay. So we have acceleration. Now we live in current epoch for cosmic acceleration. One way to see this is through observations of type 1a supernova. Type 1a supernova are not standard candles. We cannot know the absolute luminosity of supernovas. But given two type 1a supernovas, we know what are the relative luminosity between them. We can calibrate that, and therefore we can compare supernovas at very low redshift with supernovas at very high redshift and get the evolution of distances on these redshift bands. And when you do this and you compare the luminosity or the magnitude of such supernovas with predictions from a universe that it only has cold dark matter, you quickly realize that a universe with only CDM predicts supernova that around half a magnitude brighter than we actually see. And half a magnitude is a lot. We know that our systematic errors today and our error bars today, it's around like 0.05, like 10 times lower than that. And that this is a log scale, so 10 times difference in magnitude is actually quite a lot. So type 1a supernova shows that the universe is expanding, and it also shows that it's expanding with an expansion that is very close. It's close to the predictions from the cosmological constant, and that's a question that supernova can answer alone. Like, is the universe current accelerated expansion compatible with lambda? And the answer is yes. But again, supernovas can only tell you the relative luminosities between one and the other. In order to get the absolute luminosity, you need to use Cepheids and other types of candles to calibrate them. And so this year, for the first time, we published a work where we consider the joint covariance matrix between Cepheids and masers and this type 1a supernovas, so that you can get not only their relative amplitude luminosity, but also their absolute luminosity. And we show that that it's very hard for very different models of dark energy to actually shift the Hubble constant considerably. And that actually increases the probability that the Hubble constant would be resolved by physics in the intermediate or early universe. I also want to point to you, this is difference in magnitude. I want you to show that these arrow bars on the right, these yellow arrow bars, or with dotted points, if you are colorblind, and you can see that it's scattered around like 0.1 magnitude. But in the near future, with W first, you can see here the same kind of residual magnitude plot in the bottom. Is you see that the arrow bars for the next generation of satellites will be much smaller, around 10 times smaller. So this is the W first is a satellite that's gonna take data for supernova in 2027. It's like an amazing satellite, but even within experiment, you have to propose strategies. Should you observe more supernova at lower redshift, or should you try to broaden the redshift range at the expense of supernova numbers? Because to go to higher redshift, you have to spend way more time observing. And this type of question is important and depends on the type of questions you're gonna ask. Like, if you believe that that dark energy can be important between redshift 1.5 and 2.5, and I believe that can be true, and it's a logical possibility, then you're going to try to spread the redshift range more. So this type of models that I investigated, and this type of couplings between like neutrinos, inferences, and dark energy, they can affect the choices you make of the observation strategy of future experiments. So in here, it's also important to know that one question that the W first will be able to answer, and supernova can answer alone, is the universe compatible? Is the universe expansion rate compatible with a cosmological constant? And that is a question that supernova can answer alone. But suppose it isn't. Suppose we discover that the universe is that has a different W and a different equation of state, or some wild properties in expansion rate that rules out lambda. Then the next question is, what are the physical properties, the microscopic properties of the dark energy? And to answer this question, supernova cannot do that alone. To answer, to understand the physics of dark energy, if not lambda, then we need different types of surveys. We need a combination of supernova and large-scale structure. So large-scale structure, in the dark energy survey, for example, we use gravitational lensing of optical galaxies, where you have optical galaxies at very high redshift that I'm going to assume to be a perfect circle. For didactics, it doesn't have to be that way. And then we know that the light from that galaxy to us is bent by the large-scale structure, and therefore circular galaxies becomes ellipsoids, and we can use the statistics of these shapes to understand the structure formation. And why this is important? Because the combination of gravitational lensing and supernova can tell us a lot about the physics of dark energy. So let me give you a concrete example. So here I'm going to talk about the simplest paradigm of cosmic acceleration that's known. That includes the standard model. And that is a paradigm where dark energy obeys four important axioms or four important physical properties. So first, a universe in the simple paradigm is a universe where GR is the correct theory of gravity. Second is a universe in the simple paradigm is a universe where dark energy doesn't have direct coupling to dark matter besides the universal coupling of gravity. Dark energy also doesn't have direct coupling to the standard model particles, like neutrinos, for example, besides the standard, gravitational coupling. And also, dark energy doesn't collapse. So, of course, gravitational dark energy does collapse on the horizon scales. As a GR result, lambda is the only model of dark energy that has absolutely no collapse. But here I'm talking about collapse on scales way smaller than the horizon. So that means that we don't have galaxies of dark energy, clusters of dark energy. Dark energy on the universe that is well within the cosmic horizon is a universe where dark energy is completely smooth. So this is on the left you can see this is a paradigm that encompasses lambda CDM, encompasses scalar fields like the quintessence, which are canonical scalar fields, non-canonical scalar fields with crazy sound speeds, a universe with flat or curved spatial slicings, a universe with early or late dark energy. So the question is, can we falsify this entire paradigm? And it's an important question, because if any of these physical assumptions are wrong, or we can falsify any of these physical assumptions, then cosmology will look a lot different. And so how can we falsify those physical assumptions about dark energy? Well, we do this by understanding that these physical properties, they predict a consistency between structure formation and expansion rate. So here I'm showing you, that's the biggest formula of the talk. I'm showing the formula for the Fourier transform of the dark matter autocorrelation function, the correlation function of overdensities and underdensities of cold dark matter. That's the matter power spectrum. And I show you that all the components that that comes into this formula. So we have components from inflation that are shown in blue. This delta R as a power spectrum of inflation. There's also a transfer function T that encompasses physics on the early intermediate universe. But then you have this growth factor, which is a scale independent shift of the matter power spectrum. And the beauty of the simple paradigm of cosmic acceleration is that once you know the expansion rate, once you know how the Hubble function evolves in time, then you can predict the growth factor with 100% certainty. There's no additional free parameters. So you can use this consistency between growth factor and expansion rate to probe these models. And we were able to show 2 years ago that if you have a universe measured by W first with the same expansion rate of lambda CDM of our standard model, but with a growth factor that deviates from the lambda CDM by more than 5%, then you can eliminate the whole upper body of that plot. So you can eliminate all models of the simple paradigm of cosmic acceleration that don't possess significant contribution of early dark energy. So then the next question is, if this paradigm is false, what are the type of models that can predict different relationship between geometry and structure formation? And there are some possibilities. For example, you can assume that gravity is not given by GR, and DES is working on phenomenological parameterizations of the deviations of the Poisson equation and deviations of the lensing equation to see if that GR, which is the 0, part in this plot, is correct. And stay tuned for the DES Y3. We have even better results. You can also assume that the dark matter and dark energy, they have a direct interaction. So here it's a model where dark energy is a scalar field with an equation of state that is close but not exactly -1, and it has a coupling C directly coupled to the cold dark matter. And we are able to show that the DES and LSST will be able to probe this coupling to a few percent, and that's actually pretty exciting. And that's one of the projects that I'm doing with students from the DES Brazil. So that's another possibility. So here, we've done the logic of how to falsify the current simplest assumption of dark energy. If that is false, what type of physical models can explain the universe? So there was a logic in that. And here I'm going to show additional works on surveys that are related to this logic, but also have other interesting, investigations that are not necessarily related to that logic. So one that is related to this logic that we just published recently is the geometry growth split. So the idea is that in lambda CDN, we know that if you know the distances, if you know the Hubble function as a function of redshift, you can predict the growth factor with all extra parameters. So one way to enforce extra parameters is by splitting the lambda CDM parameters in geometry omega matter and geometry dark energy equation of state to growth dark matter and growth dark energy equation of state, such that the growth factor and the distances can evolve independently. So so here, for example, is what happens if you change on the right. If you see there's a solid blue and dotted blue, you can see that if you change the omega growth, and for the column blind is the lines that are connected by this arrow, you can see that you change the growth factor, which is a scale independent shift in linear scales. Of course, when it's non-linear, you have some bending around k of 0.3 and above. But that's not connected to changes in the geometry. And we have done this. This is one of the papers that I led. And we obtain interesting conclusions that show that so far they're compatible, but we get interesting error bars and to test this compatibility. And if they don't become compatible, then one of those 4 assumptions might be wrong. So that's one additional work on surveys. One thing that I'm also doing with DES, and we meet every day, and I'm helping them a lot, and they also teach me a lot of things. It's a great work. It's a great collaboration. Is the harmonic space. So harmonic space in the Y1, and I hope we also do the harmonic space in Y3 with some new tools we are developing at the University of Arizona. It's called the COA framework. And so we're going to publish soon. This is interesting data. Another interesting work that I've been done in DES Brazil is it actually involves LSST, but she's a member of DES Brazil, is the master thesis of Maria Gabriela, where a collaboration between me, Rogério, and my boss, Elizabeth Cross, we're trying to investigate how can we, the impact of baryons on future surveys, and how can we mitigate those that physics, the baryonic physics, because if you don't mitigate them and we go to two smaller scales, then you got a constraint in blue, for example, constraints that have low error bar but large bias. But once you correct for the prediction of baryonic physics, you can reduce the bias at the expense of having larger error bars. And this is a paper that we are writing soon. We already started writing, but we'll finish writing soon. We'll publish soon. We also have interesting work on W1st that about the synergies between LSST that Brazil is participating, that has large area with W1st, which will have more depth, and there's actually very interesting synergies that can allow us to probe the evolution of the dark energy equation state even more, even better than LSST can do it alone. So I have 8 minutes, so I'm just going to talk about 2 slides about other works that we've been doing. It's about statistical tensions. I love statistics, and because those tensions are not above 5 sigma or not like well above 5 sigma, then you need to use the statistics to understand and to make your bets on the standard model or your preferred model. And one of the ways that people use people try to assess those bets is via Bayesian statistics. For example, via evidence ratios. However, people are using this wrong, and I think that's something that DESI is investigating, and we also investigated, which is the following. So, in order to convert Bayesian statistics, Bayesian estimators into bets, you need a calibration. You need a scale that tells, oh, evidence ratio of 1 means that you have a 10-to-1 chance of the standard model being wrong or right. And that usually is due to the Jeffrey scale. But the Jeffrey scale depends on your prior choices. And in particular, if you make priors too wild, you can actually change this scale quite significantly. So there's this example from DESI that I show here. It's a very well-known example that you have 2 Gaussians. That could be, for example, the Hubble constant 67 versus 73, and suppose you make that measurement like 100 years ago, where we had no idea if the Hubble constant was 0 or 500 kilometers per second per megaparsec. On that context, 67 versus 73 will actually be proof or indication that the standard model is a good model, because your priors are so large. Like you have so much uncertainty. If you truly believe that the Hubble constant could be like 300, 400 kilometers per megaparsec, then if they are not the same, it's almost a miracle that they are so close to each other. We know that's not the case today, because we know that we have very tight priors on what the Hubble constant should be. And that's why a difference between 67 and 73 actually implies tension. So with that in mind, we recalibrated Jeffrey scale for the DESI-1, and we actually showed that it doesn't look like the proposed Jeffrey scale at all. It's actually centered around 6, because the price of the DES was very large, unreasonably large. And we will show that the evidence ratios we got from DESI-1 is actually pretty typical. We thought that means that things were too good to be true in the past, because an evidence ratio of 6.5 seems too good to be true. But once you calibrate with simulated data, you show that's pretty typical. And that is a work that I think needs to be done in the future for this Bayesian statistics. Or you have to use estimators that are prior independent, or depend less on prior than evidence ratios. So that's it. That summarizes the work I've been done, and this idea that you have to be very careful on how to use late time geometry and late time structure formation to probe dark energy, because there's a lot of physics before the late time that can also impact those observers. And I've been proposing this this research that tried to probe lambda with this three-dimensional, line of attack, not only with the late time geometry and late time structure formation that is usually done, by also investigating the consistency between early, intermediate, and late time universe. So thanks a lot. I'm always so please apply to the PhD at U of A. This year I'm actually in the grad committee, so I will be one of 12 people that are gonna choose the new students. So please apply. That means that there will be people in the committee that understand how the Brazilian system works. Also apply to Spionasp to work with Lehman and Rosenfeld to work with me, but I also open to create new lines of collaboration with the DESI Brazil. And if you're LGBT plus student, please don't give up. I know the times are really hard. Talk to me if you need any help. And for professors, please read that paper. This is a very interesting guide that we are trying to include those guides on the DS right now. And thank you very much.
Thank you very much, Vivian, for the very interesting talk. We now have time for questions from the audience. So please, questions.
So Vivian, I have a few questions. So first of all, thank you very much for this amazing talk as usual. And first of all, I have a question about one of your first slides. I think that you show some constraints about a kit survey on Sigma 8. And if I remember what there were, yes, there are 2 kits measurements. Why is that?
Is because kids later introduce additional infrared data from a different survey. So now it's kids plus Viking. So one is just kids, the other one's kids plus Viking, which has these infrared bands, and that's important for photometric redshift calibration.
Okay, thank you. And then some other question, maybe it's a bit off topic of this talk, but I am very interested on this thing about inflation of creating the perturbations, the primordial perturbations. And so my question is about which are the main assumptions or the, yes, that we must do in order to have a primordial power spectra as we need.
Let's see if I can answer this. So to have a power law, you need to have a slow rolling inflation. And why slow rolling? It's important to maintain the accelerated expansion. It can be broken on very short time. So I think one interesting aspect is inflation, does inflation respect slow roll? So this is a model where inflation does not respect slow roll, because these are models where, because you have some kink here in the potential, you actually generate a lot of kinetic energy. And one of the assumptions of the slow roll inflation is that all the kinetic energy from initial conditions were gone, and therefore the kinetic energy is a pure function of your position and not your kinetic energy at that position or previous position, and that is broken, and that's why it generates this interesting phenomenology. So that's one question that I think is very interesting. A second one is, does inflation is a scalar field, or is inflation is a more how can I say this, robust, or like most models in the standard models are not scalar field, except for the Higgs. There's no scalar field. So is inflation a scalar field, or is inflation needs like gauge kind of gauge models, gauge theories? And people have been investigating this, and gauge theories produce different phenomenology, not only on the primordial power spectrum, but also on the production of gravitational waves. So these are like 2 questions that I think are very hot. And the question of non-Gaussianity, for example, it's about the first one, because to get interest in non-Gaussianity, you either have to have multiple fields or you have to break slow roll.
Great, thank you. Yes. And one final question, it's about your results that you show about this reionization, your models about reionizations. Is this a patchy reionization, or is the same reionization for all the sky? How do you?
This is not patchy reionization. I think there is you can here, for example, I didn't show this slide. This is one where we introduce POP3 stars. For POP3 stars, we produce the extra reionization. There are new results from Planck 2018. The signal reduced, but it still can have a small excess, not 2 sigma excess, but it's a small one. But it can come from, for example, POP3 stars or CDM annihilation. So this is not patchy.
Okay, and so a patchy reionization can modify these plots, or no?
It can make it a function of angle. No, so a patchy reionization means that even these constraints won't be correct, because it means that tau can depend on position of the sky, and that I think may require a completely different analysis, which is very interesting. And for example, people will be using the bispectrum of the CMB to try to probe patchy reionization. There are other ways to probe patchy reionization, which I'm actually very interested in investigating.
Great, thank you.
More questions? Okay. No more questions then? Thank you, Vivian, for the very interesting talk. This presentation will be available on our website and in his YouTube channel. And for the next week's webinar, we will have LIneA Guy from the Vera Rubin Observatory talking about its Legacy Survey of Space and Time, LSST. Thank you, everyone, for attending, and a special thanks to Vivian. Everyone have a great day, and see you next week.
Yeah, my pleasure. Thank you.
Thank you.
Bye-bye.